Всем добрый день. Предлагаю начать нашу секцию.
Good afternoon. I suggest that we start our session. Thanks a lot to all of you to come here to listen to such an interesting topic as genetics. The name of discussion is quite a provocative one: how to repair incorrect genes. And today we are going to discuss a large number of questions. So we are going to discuss whether there are correct genes and what are incorrect genes, and we'll speak about how modern science treats modification of some living organisms and what it can do in this direction, including in the area of oncology, cardiovascular diseases, and so on and so forth. And our section is going to be mostly about the future, but I would like our guest today to touch upon the issues when can be useful to each of you today from the point of view of genetics, from the point of view of modern personalized medicine. So let me introduce myself. My name is Artem Yemradov. I am a co-establisher of Genotech company, which is dealing with genetics, genetic tests, and scientific research in genetics. And today we have 4 experts in our discussion, professionals in the areas: Vladimir Mironov, scientific leader of 3D bioprinting solutions; Sergey Andreev, who is head of a diagnosis laboratory of AstraZeneca pharmaceutical company; Ilya Kolmanovsky, biologist, candidate of biology, popularizer of science, selector of Primairich project; and Vadim Pokrovsky, Doctor of Medical Sciences, head of chairs of biochemistry in RDM and head of laboratories in Blokhina Center, which is related to oncology. And now I would like to ask Vadim to start from the point of view of doctor, to speak how genetics was developing, which are the key steps, and what is done for genome editing, and maybe a couple of examples from the area of oncology as well. Thank you very much. Thank you very much, first of all, to organizers for this opportunity to have the floor, and number 2, thanks everybody who came here, and we would like to not to disappoint you, to approve your visit with our speeches. I would like to start with this graph, which is quite simple and shows how during the human life, the one that we recorded, which we saw the change of expected life expectancy. This is the expected life expectancy for a person born at some specific year. If we consider the beginning of this graph, until 1900, the life expectancy was like 40, 30, 35 years, and a person can expect to live 35 or 40 years. Now we think that it's too little, because today it's almost 2 times as much. However, if we view the schedule, it's 2 times as much. That is the growth of the last 150 years. To a great extent, it was related to medicine, and I would like to speak about a couple of main medical discoveries which helped to prolong this life expectancy up to the one we have now. Number 1, this is implementation of surgeries under the control. Those who died of some medical surgeries which could not have been done without anesthesia, and in 1947 ethereum anesthesia was used by Pirogov, and he was the first to use it in a field condition, at war field conditions, and he used it at the Crimea War, and for that Pirogov got the award. And this is one of the stages which started golden age of surgery. The next thing is the discovery of X-ray. We don't have to comment upon that. That is almost all modern diagnosis, beginning of modern diagnosis. And 1900, the groups of blood discovery, and what we don't need to comment upon, this is antibiotics era in 1943 in the Soviet Union, and in the Western world we had the start of penicillin industrial production, which helped to save patients from infectious diseases. If we consider the life expectancy for the next 70 years, we see that it reaches plateau. Out of the achievements of the last 70 years, the first I would like to mention is vaccination. Here we have a figure of 1950s. Of course, vaccination was even before, and maybe you know vaccination against natural mumps. Maybe you've heard about the fact that even Catherine the Great was trying to get vaccinated against the smallpox. But the systematic approach over vaccination over life expectancy can be seen in the second half of 20th century, since there were national programs of vaccination implemented. We see tuberculosis, smallpox, poliomyelitis, and now there are 12 actually obligatory vaccinations. And after that there was huge era when they started fighting socially important diseases. What does it mean? These are the diseases such as atherosclerosis, diabetes, ischemia, arterial hypertension. And in the second part of 20th century, people became much more aware about mechanisms of development of this disease. They identified different kinds of solutions that help to cure those. And in the 90s or 2000s, we reached the situation which when we can cure or control these diseases, and it gives additional input to life expectancy prolongation. And getting to our theme of today, this is 2003. This is first complete deciphering of human genome, and this is the achievement that can be at the same line with the achievements I have mentioned, with the vaccinations, antibiotics, anesthesia, which helps further on to account on the fact that with the deciphering of genome, with the studies of the genes, we will see the prolongation of life expectancy. And I would even say, in other words, with the deciphering of genome, it became inevitable. If back in 2003 deciphering of genome took like 10 years, actually, that was multi-central research. Several countries were involved. It cost a huge amount of money, and now every person can go and decipher his genome for 60-70,000 rubles, the coding part of genomes, and it can be done within a couple of days. So the technologies are so fast, and genome is deciphered so quickly that soon we'll face the thing that new discoveries will be in the area connected to the genes that were identified. Well, what is our genome actually? This is 23 couples of chromosomes. All over there are 46. At this 46 chromosomes, we have 25,000 genes, 25,000 of coding areas, and these genes consist of 3.5 billion pairs of nucleotides. Nucleotides are just letters. Overall, there are 4 letters, and they are combined between each other in some sequence, thus creating so-called genes. These genes code our proteins, which are immediately responsible for all the functions of the body, providing the structure of the body, structure of our cells, providing for some hormone signals, and almost everything what we are proteins. When we speak about genome, and when we speak about some genetic diseases, we imagine something like this. So we think that this is something scary, remote, rare, and not frequently seen, something inborn, heavy, or something like this. But actually, genetically explained diseases are quite multiple, but for chromosome diseases, inborn distortions of circulations, monogenic diseases which are related to mutation of specific genes, there is a number of multigenic diseases, then inherited diseases at which number of genes can be responsible for development of this or that disease, and including malignant tumors. I am an oncologist, that is why it will be quite easy for me to talk about this. And if we consider all that altogether, we will see that altogether these diseases are not that rare. Actually, there is a huge number of genes which can be seen in general population and which is kind of norms. For instance, in that very oncology, there are some genes which can be mutated, like mutation of one gene does not mean disease. Distortion or failure of two genes doesn't mean disease. 3 is bad, risks are growing, and if we have 5 genes mutated, there can be a disaster. So such people who have this kind of fractures, or let us call it variations with negative result, are quite a lot. One of the ferments which is in deficit for some of the patients is glucose 6-phosphate dehydrogenase is 400 million people, like 3 countries like Russia, and these patients are those who have this mutation, and overall these are healthy people until they get some medicine or until they get some trigger, as a result of which they can have hemolytic anemia being developed. And in a number of regions this is like 40 or 50% of population. That is quite a lot. And the second example, which is not very relevant, this is cell anemia, very often inherited disease, which is related to the change of one letter in nucleotide, which substitutes one amino acid to another one in the protein, and change of the current function of erythrocyte shape. Judging by this, judging by what we know, and we know quite a lot, as I have said, genome is already deciphered, the genes are identified, we know that it consists of repeated 4 letters, and there is a great attraction to correct this. We physically understand that it's very easy. We should replace one letter with another one. Just for instance, letter A should be replaced with the letter T, and there are some complications related to the fact that it's not so easy to be done, because if we speak about a diseased person, we have several million cells, and we need to reach almost every cell and replace this letter in every cell. We cannot replace this letter in one place and leave it as it is in the other one. And when we reach into the human body, we have to change, namely what we have to change. And as I have said, that there are 3.5 billion letters in a human body. At any kind of interference, there is a risk to destroy something excessive, not what we wanted to get, and get a wrong result. And so I smoothly go to the story of genotherapy, or correction of genome, which still exists. 1990. This is William French Anderson, the doctor who in the United States of America for the first time used retrovirus adeno-associated vector. That was the first experience for the vector, could cure a girl which is with the combined immunodeficit with the aminidine deaminase deficit. This is monogenic heart disease, which is related to the scarce of this fermentation, which often finishes immortally, and the usage of this technology is kind of virus vector, which had an opportunity, which had a normal gene, and virus vector, due to the fact that it has an opportunity to build into the cell, and gene also came into the cell, and the cell was capable of synthesizing normal protein. So in this case, this is adenosine deaminase, and with the implementation of this gene with the virus vector, this opportunity became available. The second story, which also could be mentioned in the same time, the first experience of editing genomes with malignant tumors, and this was multiform glioblastoma, and they also could correct it with associated vector, implemented RNA, and tried to correct the genome. But it was not very successful, but it was the first experience of allowed medical experiment with genotherapy. The third case is actually a recent case. This is Hunter syndrome, and this is polysaccharidosis of the second type. This is a heavy disease which often results in mortal cases as a child. And here we see a person who lived after 40 years, and he seems to be quite safe. He's kind of dwarf. He has some changes in his joints, some changes of his nervous tissue. However, he suffered from this Hunter syndrome. This is also a deficit of a ferment, which can be compensated with the implementation of a new gene, healthy gene, which codes normal form of a ferment, which was done with the help of technology, which here is called zinc finger nuclease. What is zinc finger? This is zinc finger that would like to touch the finger in the necessary position, and nuclease breaks DNA, and thus it's possible to get into the necessary place of DNA, tear that, build in a new gene. And actually in 2019, less than half a year ago, we got huge press conference of doctors dedicated to this patient. They showed that the gene got into the number of cells, and now this patient has own ferment which is produced, and the illness will stop progressing. Maybe it will not be able to get back because he is already an old person, but however it is going to happen in a nearest future, like nearest 10 years. We'll be able to treat children, newborn children, and they will become healthy in case if the efficiency of this method is proven in some next experiments. And the last case which we could mention, this is the newest and relatively fresh case. Maybe some of you heard about that. That is a story about editing genome of a human embryo. It was connected to the gene which is called CCR5. This is the gene coding receptor which connects the AIDS virus while entering the cell. And this Chinese researcher had a couple of male and a female, and out of them the man was had positive AIDS, and they didn't they wanted to protect their future children from this infection. And there is scientific data to prove that there are CCR5 delta 32 mutations that make it possible to produce resistance to the entering of AIDS virus. And also there was an attempt to interfere into embryo, to edit embryons so that these girls would have genes with the necessary mutations so that they would never ever be able to get AIDS. But unfortunately, the experiment was not very ethical. Not very ethical for three reasons. Because there is a big issue of the very possibility to edit embryo genomes, as long as there is a high probability of a mistake. There is always a probability of misidentification of the necessary fragment of the nucleotide and built into another fragment of DNA, reception of incorrect uncoding genome, which in the future can give us God knows what. We can get a chimera which we don't know what to do with. And another problem which was identified, not very ethical from the modern point of view, it consisted in the fact that we got this kind of we didn't get a normal gene in all the cells of this girl, and this we didn't reach the target that we initially had. So now number of cells were preserved. Another form of this CCR5, so the growth in this or that way are still sensible to AIDS infection. It can get into the cell and continue fertilizing there and multiplying there. Some more words about this technology, which came to us from bacterial research, from microbiologist research. These are the methods that bacteria are fighting with viruses which are eating that. And this is kind of natural mechanism of protection from viruses, which was elaborated by bacteria, and this mechanism makes it possible to cut out, to identify in a virus genome the necessary part of DNA and cut it out further on with the nucleus and build in a new one. This technology, that today is less than 10-year-old, but people connect further development of genome editing with that, and researchers dealing with that in a routine mode say the following thing. Number one, they say that we know the genes that should be edited, we know the reason, and we need the failure. The second thing, we know how to do that. So roughly speaking, we have scissors, but the thing is that we do not have enough precision. So we can cut off, but we cannot cut off with 100% reliability. We cannot cut off what we want, and we cannot always put in what we want where we want. That is why for today, here we see this cage. For 3 years that guy is in jail who was dealing with the genome editing, even though the girls are healthy, but still this is a matter of time. So for today, a matter of improving this technology, and most probably in the nearest 5, 7 or 10 years we'll see possible results of using these technologies to edit a human genome. Couple of words.
A few words about the technology. What about oncology? What the problem is? Of course, this is oncological diseases, and cancer. This is the disease of genomes. In any tumor, there is some problems with DNA. The problem is that we have a relatively small number of cancers that are developed to one well-known disruption. I can refer to, for example, gene BP53. This is one of the tumor suppressors, can be mutated, and here we can have a hereditary gene that goes to Leigh-Fraude-Mie syndrome, a number of tumors that can appear starting from the early age. Maybe you also heard about Angelina Jolie, who removed her lactic glands because she had BRCA gene, that's one of the suppressors, and the mutation of it can lead to the development of ovary cancer, for example, and others can lead to some endocrine geoplasias, for example, RB, retinoblastoma, and others. There is a list of different diseases related to a particular type of mutations, but all those malignant tumors that haven't the hereditary precondition, they are usually multi-gene. It means that not just 1 or 2 or 3 genes are affected, but here you can see quite a complicated measure until those tumor cells, they progress. And as for the genome and curing of oncological disease, there are none. That could be of preventive nature as to how we can affect the genome. And those patients that have this kind of a precondition for that, we could do something. But if there is already tumor, and it's very difficult to reach all the cells and the mutation that we have, we have an enlarged map, all the dots, these are all parts that can be affected, which is really complicated. And the last slide that I wanted to mention, these are the drugs that have already been mentioned, officially registered, that are used for treating, for example, beta thalassemia, spinal muscle atrophy, and 2 others, quite rare one, orphan diseases. They can also be classified as methods of gene therapy aimed at editing your genome. As for beta thalassemia, this is we need the right of hemoglobin brain, and also here we can the second case we need to use with the transgen, with the capsid virus AAV9 and vector AAV2. This is for liver and MROS, which genes are considered to be defected. And to close it up, I'd like to say that we really know those genes are responsible for some concrete diseases. We also know where they are located. We know how many of them we have, what they consist of. We know all those options of the modified genes that do not lead to any function, disruption of protein. There could be some individual features, and we know the mutations that could cause diseases. So the problem that can be identified, edit, and adjust. As of today, there is a number of technologies that allow us to do that. They are not that apparent, not all very pretentious, and not absolutely transparent from the status, from the point of view of their status and the efficiency. But I think that in 10 or 20 years we will definitely see the result. So we will leave a little bit of time. You mentioned also anemia. You said that a lot of people work on that. But what about millions of people? Why do they have this very severe diseases? Quite nice examples. Some genes that we consider to be incorrect, still they can lead to mutation. For example, as for this anemia, cell anemia, they can also protect you against malaria. If we live in an epidemic of malaria, then this kind of genes, it can also save other people's life. And if we will say that we want to edit genes, and we say that we can identify proper or improper form, we need to be very tricky with that, because in case of wrong identification and the particular situation, yes, they can probably lead to some bad results and circumstances. For example, as for anemia, it is also used to characterize that. So you also talked a lot about oncology and also scientific specialists and doctors, but I would like to listen to Sergei Andreev, representative also of the diagnosis department, from the point of view how the different companies perceive that and what is being done in this domain. I would like to ask you, I'd like to tell us a little bit about that within a period of 7 or 10 minutes. Thank you very much for such an interesting discussion, and I would like to say that I'm impressed by the number of people. All the places are occupied, which shows that there is a huge interest for our this domain. And since we are working here, it's really nice to say that you are really interesting, and it is really nice. Since our discussion is about editing wrongful genes, but first we need to understand what wrong and what is the right gene is from the point of view of a pharmacological company. It doesn't mean that some of them should be absent and others are correct. Well, it is more than that. And that is why if we talk about the previous presentation, then I would say that it was a good insight in the history as to how you actually worked with genomes. And now the basic challenge of the past decade is what to do with the data when you actually you spent millions of dollars in order to work with those genomes and to analyze them. Right now, we are doing that at a lower price. But what are we supposed to do now with them? Now we have such a thing that is bioinformation, and I would like to tell a few words about it, how it works. So the basic points that exist in medicine and oncology. First, I will be more focused on is a targeted therapy. So targeted means that it has a certain target, certain direction. Actually, it started when certain drugs were invented, when they could selectively affect certain cells. Well, antibiotics are also targeted therapy because they use selective methods to affect certain bacteria, but they don't touch any others. And that is why, I mean, just 100 years ago, we got first chemical drugs or substances. It was beginning of a special era of this personalized or the so-called targeted approach. We also have such a thing that a personalized or precision medicine, and sometimes it is lumped together. But I would say that precision medicine is something that has its now recent achievements of the science. For example, genome analysis. You've heard about that, and based on that, they make conclusions as to what kind of methods are going to be particularly efficient. That's a personalized medicine. This is something that is suitable for one particular patient based on the portrait of the patient's I mean, proteins, genetic material, etc. This is personalized medicine. And now, I mean, to understand all those three things, they are inevitably connected to biomarkers. Well, in fact, I've been trying hard to find some kind of classification. What biomarker is? So this is any characteristics or biological feature that can be measured, I mean, in the patients. For example, temperature is also a biomarker. When you feel sick, then your temperature goes up, and this can be regarded as a criteria or a biomarker for it to be measured. They can be different. Those can point out to some disease or illness, or some of them also can have a more profound nature related to the curing effect. For example, whether a pill works or doesn't work. And the third type is when, based on the existing treatment, we can judge whether it could be efficient or not. So when we can give our results here we heard FDA, for example, company. This is one of the biggest one working in the sphere of standardization and also in genome analysis and pharmacology. For example, Food and Drug Administration, that what stands for this abbreviation. They and this is a document is absolutely available. We can have these couples between a certain drug and a biomarker and the efficiency of the two. And it includes 380 different pairs and couples that have certain links. So you see, lock and key. So they have this analysis of the targets behind that. So I would say that half of them is presented in the sphere of oncology and others as well. For example, cardio disease, metabolic diseases, and also hereditary diseases. So right now, all the molecules that are now being analyzed and developed, at least 70% of them, they are developed and related to such an approach, including biomarkers, and also it is related to the diagnostic strategy. So this is quite a modern trend, combining diagnosis. And I would like to say a few words as to how actually you choose these genes, if we talk about gene biomarkers, those that in future will show the efficiency of them, how we can filter them out of those billions and billions combinations that could take terabytes of information, how we can find the right ones, I mean these genes or biomarkers, or at least small parts of them. We have such a discipline is genomics. It appeared against the analysis of the full genome. So this is individual researches of the patients and genome of the patient or part of this genome. And after that, goes on top of that. So this is a study of DNA, and this is actually a study of the results. If it's as RNA or DNA or a protein themselves, the whole profile of it. So that can be found in that. So this is about the proteomics, and these disciplines they represent functional genomics. This is something that can actually be found at the basis of the efficiency of all those drugs for their determination of efficiency, and altogether it can allow to increase the importance of the genes during some of the diseases in case of them. If we talk about a company, AstraZeneca company, one of the active companies participating is genome analysis. We have quite an ambitious goal, a global task by 2026, analyze 2 million genomes from 2016 to 2026, including 500,000 different samples, including front-end technologies, allowing us to use the best technologies ever. We also quite sequential. This is the method that allowed us to minimize time needed for the analysis of the full-fledged genome of a human being. And when we use this kind of data, we cannot help but talk about also ways to process information. We have to work with big data and to use modern algorithm for that matter. And this algorithm allowed to identify new targets. From the point of view of genomes and the way it can be edited and be used, not just in treatment but also in search. And in fact, this is a very powerful instrument for searching new targets. I will try to explain against for example of synthetic lethal outcome. It is also needed for such a new targets. If you take three different situations, normal cell, a tumor cell, and also if we talk about a tumor cell that is meant to die. If you look at DNA inside this cell, in every single case, out of millions of those DNA foundations, you always have some disruptions and damages. It happens in healthy cells as well as tumor cells. So what is the difference between the two? We have proteins that are either in a group or on their own, eliminate those changes. Kind of do repairing works. If we take a normal cell, there are some reserve, for example, mechanism to use for repairing some damages, and their DNA can be restored and live a normal life. As for a tumor cell, unlike a normal cell, there could be and exist some hereditary mutations that, in case they are presented in a homozygote state, can turn off and cut off one of the genes responsible for reparation. So one of them is not working, you can see in the middle, but the other gene works here, and it can take on the functions of repairing of this DNA. And what would happen if this blue gene, if you use it and inhibit it, so give a certain drug that could prevent it from working. There you have a third image where none of them work, and in the results we have a big number of mutations accumulated, and a cell simply cannot survive. But it happens to a tumor cell against its healthy equivalents. It is called synthetic lethal rate, and also used as one of the inhibitors. And it is very brief information because we was informed that we were short of information. But I would like to share experience of our company. In fact, in 2018, this publication was made. In this year, it's not about mutated or inheritary diseases. We can see this information about alpha-1 antitrypsin, and against this model we managed to potentially manifest the use of this genome editing that was mentioned by the previous speaker, CRISPR-Cas. It allows us to correct fibrosis of the mice and also improve some of the indicators. It shows that technology does really work, and a number of cases potentially it can be used. So I looked at it, and in case right now there is a number, or I would say just I don't know, 15 studies maybe that are aimed at studying the efficiency of editing the wrong genes for therapy. They are mostly presented in oncology, and they are related to ABT1 inhibitor. And immunotherapy is all about that. It's not about it doesn't work, but it does really work. But this is a very labor-intensive method, and moreover, its efficiency can be compared to the standard immunotherapy. So here is the question: do we really need such a huge instrument, a whole laboratory, in order to decide on the destiny of the patient if we can use standard ways? So that is what I think is quite wondering question. So are we supposed to repair the wrong genes, or should we find the right way to them?
Very briefly, I would like to say about the fact that what we are doing in Russia regarding this. Whatever I was mentioning are global initiatives. Of course, we actively participate in genes life, in healthcare, and briefly for the last couple dozens of years, at the initiative of the company, we had implemented a program on perfection of molecular genetic diagnosis. Initially, those were patients with lungs cancer, and now more than 45,000 of people went through this research, these mutations, so that to select targeted therapy. And we made the first large-scale event in Russia with the sequencing of the next generation in the tissue of the tumor. And at the ovular cancer, this research is completed and shown at the Congress. So this is a unique portrait for Russia. It has never happened before. In routine, we use such modern methods as NGS, liquefied biopsy for the patients for this program. And having accumulated all this experience, we realized that, of course, the company wants to keep on developing in Russia. And at the end of the previous year, we have signed a memorandum on cooperation and developing of a gene panel that is a Russian solution to make those multi-gene analysis with NGS method. And at the end of the previous year, in October to be exact, in Skolkovo, we opened the Center of Innovations in Healthcare, which will make to see all these technologies alive. They are present there at active exhibition, and further on, the target is to use them in practice in healthcare, and part of those are truly innovative. I would like to express gratitude for your attention, and I'm really welcome question at the end of our discussion. Sergey, thank you very much. Can I try to answer your question with synthesis? I believe that many people in audience have a question: what out of these methods are already used in practice, and what can be available in Moscow or in other cities of Russia? What is still a scientific fantastics, or some things which are available at R&D stage, which are directly right now available right now in Moscow? So there is such a website called genome.ru, and I can share the contacts, and there is the list of innovative genetics research which are available within the frames of analysis in the state institutions in Moscow, and of course a laboratory of Onco Hospital 62 and the Oncological Center, and they have been doing diagnosis for quite a long time, complete sequencing of fragments or complete genes, and for that reason what I'm talking about is already reality. It's not the future. It's all available. We do hope, the only thing I wanted to mention, that on behalf of the state bodies, on behalf of regulatory bodies, will be cooperation not to us but to specialists, molecular geneticists, to facilitate registration of new methods, because these methods, which are actually in vitro diagnosis, they are not standard. It's hard to standardize those. It's hard to standardize the analysis of the whole genes, different to the point of mutations, which is dying like the chain reaction. And well, the more transparent and fast the procedure of registration will be, the more chances will be given to the patients. And also there will be an opportunity to get it in obligatory medical insurance policy. Our next speaker, Ilya Kolmanovsky, is doing a great thing. In a very simple language, he explains complicated things, and he is doing it in the most correct way possible. So I'd like to ask Ilya to use like 7 minutes to speak about what you think about this. Well, thank you. Thank you. As an observer, I would like to tell you a story with the eyes of one specific family, how all these methods that we discussed today and which are so actively implemented, how they are translated into specific human life. And actually, this case is related with a cell anemia, which is not likely to be related to some of the present in this room. For the USA, this is orphan diseases. There are only 100,000 people working there. This is the largest orphan disease. And in this family, two parents didn't know about this. They didn't know that they actually have this disease. Each of the parents had one broken gene, and they didn't know that they have this disease. But the first girl got two broken genes, and her erythrocytes are doing incorrect hemoglobin, and they are in the shapes of sickles and not balloons. And I believe you've heard about this, and I thought that these people cannot run well because of the anemia, but actually this is a torturing disease. They are older girl on the right of the picture named Haley. She is suffering from attacks of different pains. It's hard for her. There is a risk to lose some organs. She was not developing properly, and it was sad. Then finally they knew what it is, how that works, and they realized what you know from a school textbook, that they have 25% of a chance to give birth to a diseased person. They decided to take a risk, and this girl, the second girl, had much harder case. In the first attacks of torturing pain was at 1 year. She lost a part of her thigh bone, then spleen, and that was terrible. And there was a pregnancy, and there was the third person, the third guy, who is not only healthy, but he's potentially good donor of for one of the sisters bone marrow, and bone marrow transition created, well, terrible things. Actually, a person can be killed for his bone marrow, and this is a therapy. Will make him probably infertile in future, and he gets transplantation from donor. Sibling can be a good donor. In her 15 years, Hella was fond of children. She knew that she will have she will want to have children. She got her ovular cut out and frozen. Her bone marrow from the brother was successful. It was fatal, dangerous, and now her bone marrow is the bone marrow of her brother, producing normal hemoglobin and normal erythrocytes. And they had to solve the problem with the younger girl who could die young. And now it's 21st century. There is a method with which we can create a designed baby, and like a baby for spare parts. They took 78 cells from the mother. It's not with extracorporeal fertilizing. The father already had vasectomy, but he got his spermatozoids and got 30 embryons. Out of 30 embryons, there was not a single one. Well, you can grow them up to this stage, the stage of 14 days, and to get to know about each of them, whether they can become donor of bone marrow for the older sister. Out of 30 embryons, there was not a single one suitable, which would meet two criteria. It should be healthy, without a cell enemy, and it should be donor for senior sister. Not a single one. They sold their house. They have actually they had lots of financial problems. And now 21st century, when Dr. Stuart Orphan, who started studying this problem 40 years ago, saw first patients with hardest sickle cell anemia, only with painkillers, antibiotics in Boston, where he works. He had one goal all his life. Now he's 73. There is a classical fact, quite a long time ago established by biology, that a baby produces hemoglobin by a different gene, not the one which is used in an adult body. And the people with this disease looks like having good hemoglobin, which produced the normal hemoglobin. And for 40 years, genetics were searching for a way how to find a genome of an adult person, how to switch this on and make to work this baby gene and switch off defected adult gene. And last week we got to know that for the last year in the main children's hospital of Boston, they were fighting for this girl. She is not very happy here at the right, Helen. But she went through the following procedure. They gave her a medicine which made her the stem cells of her marrow bone leave the bones and start moving along the blood. They took from the blood circulation the stem cells, and in laboratory condition, using modified AIDS virus to deliver correct instruction, and re-educate her stem cells, making her baby hemoglobin gene to work, switch off her adult hemoglobin gene. And the next day she was under sedation with her brother sitting next to her, and he couldn't awaken her for this moment. And then he pressed the button and started recirculation of her own marrow stem cells, marrow bones, re-educated with genetic engineering. And this is an interesting story, not about corrected genes, but about the same person who had one gene switched on and the other one switched off. Next month, it was clear that her marrow bone produces healthy hemoglobin. She started running, she started dancing, she started healthy way of life, and this is the youngest patient in history who got this therapy, and this is very important. Before that experiments, there were several experiments with the adult people, and now she can become the first member of new cohort of children who will get this kind of genetic therapy. I wanted to share this because this story happened just last week, and it is interesting because it demonstrates all the palette of this method reflected in the life of a regular family. This treatment were paid by research grants of this laboratory. Nobody knows how much it's going to cost and how to make it available for people, but the whole history of medicine shows that this medicine can be exclusive and very expensive at the beginning and then become more widespread and clinical tastes related to immunotherapy of cancer, genetic therapy, and different orphan diseases. And you see that cell enemy is an extreme case from a textbook of very special people whose actual ancestors were resistant to malaria in Africa, and now they give to the city descendants this unpleasant gene. And they often say each of us during our life will finally get to know that he belongs to some of the groups of people who identify low productivity, and he will start his own fighting with the destiny. And I would like to wish you good luck in that. Thank you. Ilya, thank you very much for the story. It's truly a fantastic story and a very fresh, cool case. And just a little bit within the frames of this case, we spoke about cell technologies, and I would like to ask Vladimir Mironov, who is scientific leader of Britex Solutions, to speak about experience of this company and how genetics can actually help in this issue. And right before the new year, I was in this company in the laboratory, and I was truly impressed. The things that you are doing there are truly cosmic. Could you please speak about those? Well, our company, of course, is not dealing with genes immediately, but as you know, there is kind of theory that gene ferment, Samendis, well, we are trying to print human organs from the cells of a human, and if we use autologic cells, those are the cells of the patient himself, we use the same genes. Though there are three main sources of genes to print bodies. The first one, embryon stem cells, that is truly good. In my case, it's too late. 65 years ago I had to do that, and I can use only allogene cells which can cause immune response, and in many years the usage of embryon layer of cells is prohibited, especially in Catholic countries. A couple of years ago, a Japanese scientist, Yamanaka, showed that we can take like biopsy of a cheek and identify a fibroblast cell, add 3 or 4 genes, and you can get so-called induced manipotent stem cell, which behaves in the same way as embryonal stem cell, but this is autological. But here we have a small question, which I suggest genetic specialists to discuss. Well, in order to make this, we should add 3 or 4 genes. And number 2, in order to direct this cell to thyroid, there will be 6 times gene therapy. And to believe that nothing happens to other genes, it would be quite naive. Well, at least in 2004, when for the first time the cornea was transplanted to a woman and she started seeing, then the second woman immediately got mutations and they stopped that. And now please let me show you what we are doing. And basically our company exists for 6 years already, and here are our main achievements. Why do we print organs? Because only in China there are 2 million of people waiting for a kidney for transplantation. Kidney transplantation costs $250,000. So 2 million multiplied by 200 by this is the market only for China. So dialysis, it's 6% of expenses for healthcare in the USA. This is a very expensive procedure. If we know how to print body organs, then expenses on treatment for kidney diseases will be decreased by 50%. There will be no need to use autological cells, but we will use immune suppressive. There will be no need to use dialysis and immune suppressive drugs. And also there will be a new industry of organs printing. So this is so-called win-win-win situation. 15 years ago, we believed that we can print an organ. We take a cell, we make a kind of sphere of this called spheroid. Spheroids can get connected and can merge, and if with the help of robot you put it in a correct way, you can print an organ. How is it going to look in the future? We take biopsy of fat cells brought into the machine, which is called clinical sorter, cell sorter, and directed to another machine making spheroids, then robotic bioprinter, printing organs, and then perfusion bioreactor where it matures. These elements exist separately. To bring them together, it's kind of factory on producing of human organs. Well, this is how the spheroids look like. Spheroids or bubbles made of fibroblast skin, of human skin. Pay attention, they are all very round and they are of standard shape, and we can make them unlimitedly. This is the main device, which is called bioprinter, which consists of a robot which moves 3 dimensions from dispenser or syringe, and of course there should be a robotic control system like computer and collector. So this is the first native Russian bioprinter. We called it Fabion, fabrication, biology, and this is among 5 best bioprinters in the world according to independent assessment, and as to functionality, the first position. We have 5 nozzles. It can dispense separate spheroids. And of course, when we have spheroids, that is construction units, when we have a printer, there is a question of what we can print. And of course, we would like to print a kidney, heart, or liver, but all that is very expensive. That is why we decided to print the easiest body, that is thyroid. Bacteria, arteria, number of follicles, and vein. This is the whole thyroid. And see how the separate follicles look like, which synthesize thyroxine hormone. Every follicle is covered by a net of capillaries. And this is the scheme of our experiment. And we have identified the beginning of thyroid, made spheroids out of this. And you see the first printed live mouse embryo body. If I said human, well, it could have been much better, but unfortunately, even though the article that you can add 2 genes from induced stem cells and make epithelium of thyroid was published in 2012, 6 years they cannot translate mouse into humans. So we're waiting for these cells from Belgium, from Japan, from other countries, and until now it's not available. How to prove that this is functional organ? For that reason, well, my clicker doesn't work. Okay. Well, so, in order to prove that thyroid works, we only need to irradiate it in the same like Chernobyl, and it will totally disappear. The level of thyroxide in blood will go down, and if we change this, if we transplant it, and the level goes back, and we check it. So, we have printed the mouse thyroid, and the level of thyroxine T4 grew by 50% in control, and if you consider histology, it's 1:1. So here in Russia, for the first time in the world, in 2015, we printed functional organ. What we can do next? There is such a guy, Andrei Gain, who is now a citizen of the Netherlands. He lives in Manchester, and he got 2 prizes, a Nobel Prize for graphene and Nobel for this flying frog. And the question, what for a frog needs to fly in high magnetic field? When he made this experiment, he never got an answer. But we decided that actually, if we use magnetic levitation, especially in the space, then we shouldn't need so-called toxic substance, but these are so-called details, get a line. And we can make an organ within 30 seconds, in the same way like bees.
Or, for example, like that. So we refer to this as magnetic levitation or magnetic fabrication. Here is our experiments. We used hydrogel, and they flew to the cosmic space station, and then put 2 magnets. They were put together with formalin, and then delivered everything to the ground. So here is the experiment. So this is our hydrogel. This is a device that we call cheburek, but officially it's organ out. You have 6 ports here for 6 experiments at the same time. Now that's what it looked like. I mean, design of magnetic bioprinter organ out, and the result doesn't work. For the first time ever, we, on board of a space station, in Russian segment, we printed a cartilage consisting of spheroids that was made with the help of magnetic levitation, and we were 6 months faster than Americans. But it turns out that we can make this levitation not only just with the help of magnetic fields, but also with the help of acoustic. You can see that they can fly and assemble in this way. And some French state that if you could do it, we can also use use it for the cortex of the brain. We decided to make a tube. That's what it looks like. This is a long tube, and we managed to use a superconductive magnet, which cost $1.5 million. Then we can print anybody organs of any complexity within a period of 30 minutes. Thank you very much. It's me. Thank you very much. Vladimir mentioned several times that some things are done for the first time ever, and from my perspective, the team, it's really, I mean, of an international scale. We understand that there are not so many centers in Russia, but still they exist, and we just have a little bit of time, 7 minutes to allow our listeners to ask questions, and please specify the speaker you want to address your question to. Who would like to answer a question? The first question goes for Vladimir. Thank you very much for such an incredible message. Short questions. So, hypothetically, theoretically, when will your dream come true? I want to do it in real life. And the question for Sergey. That was a brilliant presentation, and here is my. The point is that we cannot find a special guideline that would tell us that could it be used for experts. It's like a genetic portrait. So there is a concrete definition to describe that it can be used for that matter. Are there any guidelines to do that? No doubt, there are a lot of them, those classifications, and I'm ready to share that they are different. But as a company, I can tell you that we work with precision medicine, so we're looking for the factors where it could be particularly efficient for the patients. But in classification, we have a lot of them. And as for personalized medicine, the main feature of it is that we have a concrete patient that undergoes some study, and based on the full portrait of all the possible characteristics, we choose a drug that would be particular suitable for the treatment. Again, my question, where it is written transparently. I told you I can share my information. Okay, let's do it later. Good afternoon. Thank you very much for such a lecture. I have a double question. have already seen this breakthrough, or do we have to wait a little bit of time for us to understand that implementation of the gene of this repairing works could lead some distortion of the system later on? And the second question, if you want to repair a wrongful gene, not so much is to blame for bringing, but it's more about the gene, but it could be also done within this format as well. Speaking about genes and upbringing, well, in fact, we in our laboratory we work with a psychiatrist, and also we are part of a consortium of psychogenetics, and a lot of different studies show that when it comes to this psycho disease and etc., genetics works perfectly fine, but they are quite complicated in terms of treatment. For example, hereditary disease. When we have a mutation and something goes wrong, if we could talk about schizophrenia or depression, these are some problems with the genome and the sequence, and it is very difficult to read it and analyze in advance. But the good news is that if we understand that there is some genetic loads, or for example a person tends to demonstrate certain behavioral patterns, then we think that there are some environmental factors that can affect the situation, and the contribution of the genetics is not that big, and you can modify these external environments, changing it, but without changing the genes themselves. So we also have some extreme cases when combination of genes is where we want to change the environment, but the behavior is, it's pathogenic, and there could be some serious disease that can be hardly modified. But very often it's all about combination of genes, so it's not a real sentence, and you can modify that. Thank you very much for the lecture. I wanted to ask you the following. A lot of been said about nutrigenomes mix. What about the impact of food on genomes? For example, methylation of genes. In some products we do have these components that have this kind of positive effect. So with the help of food it's possible to feed a little bit genes. I don't believe in that. No, as observer I don't believe that, and I won't find it in journals or magazine of any kind, international. And a question for you, just a short question. For example, we decode it and we understand what went wrong, for example, what we need to repair. For example, there is a gene anemia, for example, we need to repair it. Wrongful watermelons and we identify the time limits. 105 years old, doesn't matter. And the second, how far can we come to a situation where we can use this gene to affect not just the psychological but only physical parameters, but also emotional ones? As an observer, I will say a few words. We have to understand we have quite special heritage. We haven't been exposed to natural selection for quite a while. In the population, you have those mutations accumulated. For example, 100 or 70 letters. It's like it be compared to those mutational processes that were wrongful. Usually we just have one copy, and it's not always correct. So we need to work with something that we got. It doesn't matter what kind of external factors there are. Like for example, heavy metals, even though that it shouldn't be underestimated. And as an oncologist, I can add over those heavy metals and radiation, there is a risk risk factors, cancerogenic, which are chemical substances, for example, aniline beta's that led to bladder cancer, where they work with tissue. For example, those who worked with asbestos, they had a higher risk of the pleurum, mesothelium, a number of factors that apparently lead to mutation and can trigger some disease. Don't forget about Santa Claus cancer, ovary cancer, because they were Yes, exactly. Here we have two different stories. The first one is the risk, and the second one is congenital sensitivity to some things. For some of the patients can be exposed to short-term exposure, and others can live longer. It's good from the scientific point of view, and not from the scientific one. When, for example, at Chernobyl, a lot of people found themselves within the zone of radiation, and a lot of eliminators were there. There were different effects. Some people died very quickly, some people died very fast, and some are still alive. It's all about dosage, and also individual sensitivity. All those cases prove that, yes, parents are the most toxic people, and so hardly anybody was in Chernobyl, but those who inherited from. Do you have a question? So unfortunately we ran out of time, but we still have the speakers and you can communicate with them a little bit. Thank you very much. У нас опять нет времени?